Hi, this is Miss Litton, and this is Honors Bio 7th period review, getting ready for our final for Unit 7. Say hi. Hi. We have already reviewed Unit 5 and Unit 6. Both of the recordings from YouTube can be found on my YouTube channel, as well as in your Google Classroom, as well as a PDF of both presentations. So this particular unit, when I set up the top 10 things, the 10th thing was additional objectives, and like I told you, that's not going to be on your test. So the first thing was structure and function of blood vessels and heart chambers and valves. So in your mind, name the 3 blood vessels, tell how they are different anatomically, tell how they are different structurally. Start running that through your head. Okay, also you want to think about the chambers and valves of the heart. Start to think, what do I know about that? Okay, the second question is about blood, or things to know are about the pathways. I would say systemic and pulmonary, or I would, differentiate between those two. What's found in blood, remember road trip, okay, and disorders when things go bad, all right? So starting to think about those things, tell the person sitting next to you what is the least familiar and what is the most familiar to you of those things. Go ahead.
I know the chamber. Oh wait, I think I named all the chambers. Name the chambers. I didn't name the ones that are in.
So this is a jam-packed, right, unit. We have 4 big systems in this one, so let's start working through. Arteries, veins, and capillaries. By definition, let's do our song. Arteries go away from the heart, veins go towards. Arteries, arterioles, capillaries in the middle, venules, veins. Heart, body, heart. I meant to do it the other way. Heart, body, heart, lungs. Heart, systemic, heart, pulmonary. Atria, I'm talking about the heart. Atria, collect, and ventricles pump. Good, okay, that's a big ticket there. Arteries are thicker, why? Higher blood pressure, because it's going away. Okay, hallmark of capillaries is they are 1 cell thick, because that's where all exchange takes place. Veins have something. What's unique to veins? Not as much muscle, but they have what in them? Valves. What do valves help? Keep blood flowing in one direction. Good job. All right. Here we can see where the capillaries are. Not all your blood is in every capillary at every moment. There's little sphincters that shunt them to different directions. Chambers of the heart. Let's label them. What is this? Right atrium. Okay, good. What do you call the valve right here? Tricuspid. And that spells? And this one is? And that spells? And then what are the valves right here that are leaving the left ventricle and leaving the right? Semilunar? Good. And so the flow of blood, right, is in, I meant to be blue. Is venous blood blue? No, that's just a misconception. It looks blue underneath the skin. Right atrium, down through the tricuspid valve, right ventricle, up and out the semilunar valve, out the left and right pulmonary arteries, because arteries go away from the heart, carry deoxygenated blood, because this blood came from your body. This is the superior vena cava, inferior vena cava, right? Deoxygenated blood coming back from your body. Okay. Left and right pulmonary arteries, arterioles, capillaries around the alveoli of the lung. They come back oxygenated. In your left and right pulmonary veins. Good, because arteries go away, veins go towards. Remember that? Okay, and why do I say left and right? Because you have left and right lobes of your lungs, right? Left and right on your lungs. Remember your lefts and rights, it's on you or on your patient's left, your right. Do you remember that? Okay. and left atrium through the bicuspid valve, left ventricle, up and out the semilunar valve, and then out the largest artery of all, which is your aorta. That's where the blood pressure is going to be highest. The left ventricle is stronger than the right ventricle. Why? Has to pump to the body, whereas the left ventricle only has to pump to the lungs, right? Distance isn't as great. All right, remember, and those are the chambers of the heart. I mean, if I asked a question, maybe one or two questions, but hopefully you remember that from that review. What's the separation between the left and the right? Septum, just like your nose, okay? And there's an inside picture, but we already did that. Pulse, remember, is the expansion of an arterial wall against your fingertips. What does your pulse tell you? How fast your heart is beating. Because what's generating that pulse? Your heart. No, your heart's beating, and then the blood's going out there. And it's snapping back, right, to keep the blood flowing in one direction. Systemic and pulmonary. Pulmonary circuit is the deoxygenated blood in your heart going to your lungs, getting oxygenated, and coming back to your heart. That's your pulmonary circuit. Anything to do with lungs is pulmonary. Doesn't matter if you're in an artery or a vein, right? But anything when the blood is going towards or away from the lungs, it's pulmonary. Yes? Okay, systemic is basically everywhere else. And we talked about there are specific regions that we learned about. The circulation of the systemic around your heart is called coronary, right? Remember that? Do you remember your hepatic portal vein? Remember how your blood gets shunted from your small intestines and stomach to your liver before returning to the heart? And the reason for that is what? Discuss with your bio buddy. Why would you shunt your blood from your small intestines to your liver before returning to the heart? Keep going. If you haven't eaten in a while, then the blood will be what? Low in sugar, so your liver will add to it, right? If you have eaten, then your liver will pull out excess and store it. Okay, good. Next, that exchange at the capillary. It's competition between two pressures, okay? Remember, only at the capillaries can you ever exchange anything, and that is because, why? One cell thick. Yeah, one cell thick. So it doesn't matter if I don't have a capillary right here. It doesn't matter if I have a big old artery traveling up here. I need a capillary in order to distribute nutrients and oxygen and pick up CO2 and waste, right? Only occurs at the capillary bed. Now, along the length of the capillary bed, the distance of the capillary bed, the hydrostatic pressure, the force on the blood due to the heart, is going to be closer to the heart, right? At the arterial end of the capillary bed. It's going to decrease as it moves farther away from the heart. The blood pressure is going to go down. That's logic, right? The osmotic pressure stays about the same. It's due to all the things dissolved into blood. Let's go ahead and address that right now. What is dissolved in blood? Well, there's the formed elements. Can you think of the formed elements? Turn to your bio buddy and see if you can come up with the formed elements. Did they say red blood cells, white blood cells, and platelets? And what's the job of red blood cells? Carry oxygen, right, for you, transport it. White blood cells, fight, platelets, blood clotting. Those are the formed elements. Then other things are actually dissolved in the blood. The rest of the blood is mostly water, which we call plasma. Okay, to think about what's dissolved in plasma, let's go on a little road trip. See if you can come up with everything with your bio buddy. Did you come up with 7? 7? Okay, so let's talk about what's dissolved in plasma. Gases, nutrients, salts, proteins, nitrogenous waste, hormones, vitamins. Yeah, we totally got it. All right, so the osmotic pressure is pretty continuous throughout it, but since the hydrostatic pressure is greater than the osmotic pressure at the arterial end, that facilitates pushing fluids out with all those nutrients in it. By the time the blood travels to the venule end of the capillary bed, it's lost a lot of pressure. And as a result, the osmotic pressure saying come in is greater. So that's when you recover CO2 and waste at the venule end. It's a very delicate balance between those two pressures. All right. We just did that, didn't we? Okay. Right now, before we go any farther, check with your bio buddy. What of that do you think you need to spend a little more time on right now? Go ahead. What do you need to spend a little more time on to get ready for your final? Okay, moving on. Next system. Look to see these three topics. Okay, ping pong back and forth. What do you remember in general about 3? And one of you, what do you remember in general about 4? I don't care if somebody goes first. See what you can remember without looking anything up. See what's in your brain already. Go.
Non-specific defenses you
Oh, right.
skin, stomach, hair. I don't know. I think
All right. You ready? Okay, come back to me. Non-specific defenses. Everybody has it, right? Innate, born with. Remember, our first thing we try to do is keep things out of our body, right? What kind of things do we use to keep things out of our body? Skin, hair, mucous membranes, cilia, low pH. Exactly. All, yeah, good bacteria taking up spots so bad bacteria can't. Those are all things that we use to keep out of our body. But if it gets in, our innate immune response is what we're born with. All it knows is from self, from non-self, and can attack it. What can't it do? It can't learn. Only your specific immune response can learn. Only your acquired immunity can learn. And that's with your B cells and your T cells. When we either fail to attack something we should or attack our own body parts that we shouldn't because they belong to us, that's when you have side effects of our immune system. So let's get into some details here. The first thing we need to remember is at the capillary bed, you have lymphatic capillaries, potentially, and lymphatic venules that are right there with your circulatory system, right? Right at the capillary beds of your circulatory system. And we know that delicate osmotic balance that we just discussed, hydrostatic pressure pushes fluids out of the capillaries and osmotic pressure draws it back in. But it's not even Steven. More gets pushed out than gets drawn back in. So the excess fluid, we got to get it back in our circulatory system. Your lymphatic system will pick up that excess tissue fluid, pass it through lymphatic vessels, pass it through your lymph nodes before returning it to your circulatory system. So lymph nodes are like border crossings, and that's where your specific immune response cells can hang out and be like, oh, is there anything bad here, anything foreign in here that we need to take care of, okay? Next, when we talk about the organs of your lymphatic system, your primary ones, bone marrow, because all blood cells come from your bone marrow, but specifically your B and T cells come from your bone marrow. B cells are called B cells because why? They mature there. Whereas T cells leave the bone marrow and they go mature in your thymus gland, which is on top of your heart, which is bigger when you are a kid. Yeah, Then you have lymph nodes, which filters your tissue fluid, your excess tissue fluid that got shoved out at your capillary bed. Your spleen, however, filters your blood. Exactly. And then we talked about things like tonsils and Peyer's patches maybe in the intestines. There are other patches of lymph, that was an apper. Other patches of lymph node tissue as well. So if we look here, we can kind of see the origin of some of those cells. When we look at a blood stem cell, a myeloid stem cell, here are those red blood cells, one of the formed elements we talked about. What's the job of a red blood cell? Carry, yep, platelets, blood clot, these right here are part of your general innate immune response, right? These are the things, which of these is most common? Neutrophils, 70% of your white blood cells. These are your policemen. They're just trying to kill anything that's foreign. Your lymphoid stem cells lead to your B lymphocytes and T lymphocytes. Then we talked about how some don't go to the school of thymus, so they pose like T cells, but they're not really. B lymphocytes, these are the guys that secrete antibodies. T cells do cell-to-cell combat. So they attack our own body cells that have gone bad, either due to cancer or they're infected, right? So they're cell-to-cell combat. T cells, T, fight, right? T, I look like a T. B cells release what? Antibodies, like a swarm of bees throughout your body, right? And they go and attack anything, attach, and mark something for destruction. I already did that. Okay, skin keeps things out. Enzymes, hairs keep things out. How do you know who the invaders are? Surface markers. Every cell has antigens on it. Those antigens either belong to you or they belong to someone or something else. Okay? If they belong to us, we have learned not to attack them unless we have a disease, right? An autoimmune disease. Something foreign, that's what we do want to attack. So who do we call? The good guys. So here are your police force. Some key guys in here would be like a macrophage. Do you remember what a macrophage does? It releases what? Oh, I don't know. Macrophage eats. Good. Mast cells do what? Histamine. Sorry. What do dendritic cells do? Eat, right? Eat debris up. Natural killer cells kill. Basophils in your blood kind of do what your mast cells do, releasing histamine. Complement, do you remember what they do? Drill holes. Neutrophils kill. Eosinophils kill as well. If we look over here, B cells are the one releasing antibodies. T cells do cell-to-cell combat. And the natural killer cells were T cells that failed school of thymus. When we look at the players of the general immune response, the innate immune response, neutrophils are big guys. Macrophages get there a little bit slower. Remember, they start as monocytes, but due to histamine, which makes blood vessels leaky, they can crawl out a little bit easier and grow into great big macrophages and eat, and dendritic cells eat as well. Inflammatory response. That is a sign that you have an infection. So histamines makes your blood vessels leaky, which then hydrostatic pressure forces a lot of extra fluid out, which causes swelling, excess heat to helpfully kill off the bacteria, right? And makes it easier for other organisms to get there. When you have allergies, like to pollen, you are getting all upset with pollen, okay? And your body is responding as if it's something that can really hurt you, when usually it's your own response that ends up hurting you, your overreaction to that pollen, or peanut butter, or bees, right? Those are all kinds of an over-response of your immune system. Antigens we've talked about, okay? Before I unclick this, whoever's in the blue seat, you are the antibody-mediated seat. Try to remember what should be here. And in the slate seat, you be cell-mediated. Try to remember what's there. Go ahead.
That's like B cells, they target.
Did you do a good job?
Yes.
Okay. Remember, antibodies are Y-shaped, right? Antibodies are Y-shaped. 2 arms. They can attach onto 2 antigens at the same time. All right. T cells. How do you know what cells to attack and what cells not to attack? Remember those antigen presenting cells, like a dendritic cell? They'll go and find a bacterium, a virus, overtake it, kill it, and cut off its head and show it to you. What do they show it to you on, an MHC1 or an MHC2? MHC2, I will what? Help you. If a cell is infected, they can't keep their mouth shut. They also display it, but they display it on an MHC1, and you are done. Okay? So that's how T cells know. You're a good guy. You're okay. I won't kill you. You're out there doing the good fight. You're infected, so I'm going to kill you. By how you display the antigen, okay? Knows whether to keep that cell or get rid of it. So you're safe and you're out. What kind of things trigger responses? For T cells, it has to be presented on an MHC1 or an MHC2. For B cells, to start their response, they have to be exposed to the actual antigen on that virus or that bacterium. Remember B cells? What kind of cells will come from B cells, a stimulated virgin B cell? Plasma cells, which release antibodies, and memory cells for next time. Whereas when a T cell is stimulated, it will make what? Cytotoxic T cells for killing. What else? Helper T cells to amp up the immune response, like with cytokines, and memory cells for next time. Good job. Okay, you good with that? Of course you are. Okay, immunity that we're born with is our police force. B and T cells are acquired. Anything from B and T cells are acquired. Either you actually got sick, you were exposed to somebody who was sick and you triggered your virgin B's and T's, or you got a false sickness. You got a shot of polio or measles. So you weren't going to really get measles, but you were going to develop B and T cells from it. If you don't have time, because it takes 10 days minimum or so to develop your B and T cells, and you just got exposed to something really bad, that's when you can go get a shot of gamma globulins. Or a baby who doesn't have time to get his immunity up for everything that's out there in that world gets the borrowed immunity from his mother's breast milk. Okay, before we go on, tell your bio buddy right now, which of those things do you think you need to review a little bit more? What do you need to review a little bit more? Okay, so now comparing nervous versus endocrine, protein versus steroid hormones, positive versus negative feedback, and contrary hormones. Then reviewing the glands, where they're located, what hormone and what they do. Okay, so the first thing, nervous versus endocrine. Which one's faster? Nervous. Nervous is faster, endocrine is more long-lasting. Protein versus steroid. Which type of hormone, what kind of hormones do we have more of? Protein hormones. Do you know where steroid hormones come from? Gonads, testes, and ovaries, right? Those are steroid hormones. And from your adrenal cortex, glucocorticoids, mineralocorticoids, cortical sex hormones. Those are the only ones that are steroids. All the rest are considered protein-type hormones, right? So which one gets to go all the way into the nucleus? Steroids. Because steroid is a type, it's under the umbrella of a what? Lipid. And what kind of cell membrane do you have? Phospholipid. So steroids can go through the phospholipid bilayer, go all the way into the nucleus, and usually impact transcription and translation. Their effects are long-lasting impacts. Whereas protein hormones stand at the door and knock. They don't actually get to go in, but they trigger a response inside, and that response inside or comes inside is called the second messenger. The first messenger was the protein hormone. The second messenger could be calcium or cyclic AMP, something that's inside the cell, okay, which effects are a lot faster. All right, let's take a look. So exocrine glands, endocrine glands. Exocrine glands secrete into ducts and vessels like a sweat gland. Endocrine glands are different. That's because they put the hormones right into your blood. Okay, an exocrine gland is to exit out of the body. Salivary gland would be an exocrine gland. It's secreting saliva into your mouth, right, and eventually it's going out of your body. Endocrine gland goes into your blood. How it works. When that hormone is released and it's carried by your blood throughout your body, the only cells it will impact are cells who have what? Receptors for that hormone. If you have a receptor for that hormone, it will trigger some reaction within that cell. That's why hormones can work anywhere in your body. It might be secreted from your thyroid gland, but it's only those other cells in your body who have a receptor for thyroid hormone to trigger any action within those other cells. All right, we already compared nervous and endocrine. Positive and negative feedback. Which one amps it up, amps it up, amps it up? What would be an example of positive feedback? Giving birth, right? Negative feedback keeps it just right, okay? So kind of, it will lower it back down to get it, or increase it if you need it to be higher. Contrary hormones do the opposite. Whereas insulin lowers blood glucose levels, glucagon will do what? Raise blood glucose levels to keep it just right. Here's your positive feedback. Too much hyper, too little hypo. Whoever, let's see, in the slate seat, why don't you differentiate between these two? We've already talked about it, but I yow it. Go. Finish up. All right. Now, I'm not going to go through all the glands and everything. I'm just going to hit this one big ticket one, and then I'll let you review the others. Okay? So, your hypothalamus is in your brain. Your hypothalamus is connected to your pituitary, directly or indirectly, depending on which lobe it is. Okay? The posterior pituitary descended out of the hypothalamus like a testy would descend down. Okay? And so the hypothalamus is directly connected to the posterior pituitary. The hypothalamus makes the hormones that the posterior pituitary secretes. The posterior pituitary hangs and stores onto those hormones and then releases them when the hypothalamus tells it to do so. Hormones of the posterior pituitary, oxytocin and ADH. Remember what oxytocin does? What does oxytocin do? Baby out and milk out. That makes sense, right? Because if the baby comes out, you got to give it some milk. Okay, so we're going to remember that. And ADH stands for anti-diuretic hormone. What does that influence? Anti-diuretic hormone. Kidneys, right? And the collecting duct and reabsorption of water. Anterior pituitary did not come out of your brain or your hypothalamus. It crawled up and out of your what? Mouth and grabbed on. And so this is one of three places where you have double capillaries. One is in the kidney, two is in your hepatic portal vein between your intestines and liver. We talked about that, and here's your third one. You have releasing hormones, which are put into the stalk of the pituitary in the first set of capillaries. They are carried to the anterior pituitary. Second set of capillaries where they trigger the release of particular hormones. And here they are. What is TSH? What is that?
Thyroid.
Yeah, so when thyroid stimulating hormone comes out of the anterior pituitary, that's because thyroid releasing hormone came from the hypothalamus, yes? And that's going to stimulate the thyroid gland. Adrenocorticotropic hormone stimulates the adrenal cortex. Prolactin, production of milk. Prolactin, I am pro-lactose, make the milk. When I want the milk to come out, that's a different hormone, oxytocin. GH stands for growth hormone. FSH and LH are gonadotropins, stimulating your ovaries and your testes. That is the most complicated of all of them, right? So I just wanted to go over that one with you. This is a really good example of negative feedback and relating to the hormones we just talked about. The hypothalamus secretes thyroid-releasing hormones into the capillary, the stalk of the capillary. Then the anterior pituitary secretes thyroid-stimulating hormone, and that targets the thyroid gland. Thyroid gland starts secreting thyroid hormone. What else does a thyroid gland secrete? Not that one, a different one. Calcitonin, tone it down now, right? Lowers blood calcium. But anyway, as this thyroid hormone level is secreted and you get more and more and more and you get enough, it shuts down the hypothalamus, the pituitary. What kind of feedback is that called? Negative feedback. Go. This is just showing you the glands. Fight or flight, epinephrine, norepinephrine, or adrenaline, noradrenaline comes out of your adrenal medulla. That's right now, fight or flight stress. Long-term stress, like a semester of biology, that's coming from the adrenal cortex on the outside. We know about the pancreas, insulin and glucagon. We already talked about that. Pineal gland is your third eye. It secretes melatonin. Yeah, and that helps you with your sleep, right? As you sleep, melatonin levels go up, and when you get exposed to light, melatonin levels go down. Then there are other things like adipose tissue, which signals when you are full. Yeah, you can review those if you want to. Last but not least, another big one we have is the nervous system. So there are the divisions, the functions, structures, action potential, synapse. So let's try to in on those right away. So we have sensory neurons that go towards your central nervous system. Motor neurons go away. And so sensory and motor, and then your central nervous system, your brain and spinal cord, consists of what two things, or consist of what kind of neurons? Sensory, inner neurons, and motor neurons go out. So your brain and your spinal cord are all interneurons. Okay? When we talk about arresting potential on a neuron, how it fires, the outside is what charge when a neuron is at rest? Positive. And the inside is negative. That is due to the pump. What is that? Sodium potassium pump. So it pumps 3 sodiums out for every 2 potassiums in. Okay, and that happens a lot. Okay? That happens a lot on both sides. So there's more positives outside than there are positives inside. So that's a differential. What else makes it, besides a difference in positiveness, what else creates that potential? Leaky potassium gates, some potassium leaks out. What else? Negatively charged proteins that are on the inside. That is the resting potential. A neuron at rest is negative inside, positive outside. If you can trigger an action potential, okay, due to something at your synapse, some neurotransmitter, what gates get opened first in an action potential? Sodium. So sodium starts coming in, and all of a sudden now the charge on the inside is now positive. That is your action potential, the reversal of charge. You get from point A to point B. Then down here, this sodium will change to, there'll be calcium out here. It will come in. It will cause synaptic vesicles to fuse with the presynaptic membrane and release a neurotransmitter across the cleft. But as soon as sodium's coming in, there's a quick fix to this problem. What's the quick fix to the problem? To restore the resting potential. Potassium goes out. Good. But if that keeps happening, you'll have a bunch of potassium out and a bunch of sodium in. So who's our long-term fix again? Sodium potassium pump. Who pumps sodium out and potassium back in. Okay, and I have videos just on action potentials and recovery, just on those topics if you want to go over it. You can see here, the inside is negative, depolarization because sodium comes in, repolarization because potassium goes out. At the synapse, neurotrans right here, calcium comes in, causes the synaptic vesicles to fuse with the presynaptic membrane, releases its chemical across the transmitter. If it's excitatory, it could start opening up sodium gates. If it's inhibitory, it starts to close them. Central nervous system, brain and spinal cord. Peripheral nervous system is all your nerves, right? That are located outside of your brain and your spinal cord. And if we look at those, some come off your cranium, right? And some come off your spinal cord directly. When we look at them, sensory go towards, motor go away. Let's pay attention to this, somatic and autonomic. Which one do I not have to think about? Autonomic, right? You are not having to tell your heart to beat. You are not telling yourself to breathe. You are not telling yourself to regulate your temperature. It's doing all of that for you, right? Somatic is choice. You're choosing to sit up in your chair and not fall on the floor. You might want to fall on the floor. You might want to pound your head against the desk. But yet you're going, social norms dictate that I don't do that right now. But this is what I want to do because I'm tired of listening to this. That, right? What you're doing right here, that's choice. That's your somatic nervous system. Autonomic is what you don't think about. And you're either under sympathetic, right? The reason why you're here right now is you're hoping you're not stressed out during your final. Okay, that would be your sympathetic nervous system. What you really want to do right now is parasympathetic, rest and digest. Okay, so it's a balance of these two in life. All right, a reflex arc. I touch a hot pan. I touch a scalpel. Something causes pain. Sorry, two kids do that today. Okay, touching sensory neuron goes in. Synapses immediately with a motor neuron, so I can pull away. And also synapses with an inner neuron here in my brain telling me, ouch. It just helps us, reflexes help us to respond a lot faster. Okay, here's a little diagram to review what we just talked about. And you don't need to know your additional objectives. Good job. I'm proud of you. That was a hard push. Now, when's the next time we review? Friday, 7th period. Do you know that I love you? Okay, study. Have a piece of toast if you want it. Oh, look at that timing. Can we just appreciate that for a minute? Okay.